Hello everyone. Thanks for joining this session. So today I will be talking about scaling AI with silicon quantum advantages. So what are the advantages of going with silicon AI with silicon quantum advantages? So it's an executive technology strategy. It's a part of the strategy that synthesizes silicon quantum progress, AGI, is scaling in constraints and pragmatic pilot roadmap. Having said that, let's go in detail. Why silicon-based quantum computing is required. CMOS compatible path to scalable higher density qubits. As part of the silicon based quantum computing, in compatibility with existing CMOS semiconductor manufacturing uses current fab process and standards. So it uses the current fab process and standards. Higher qubit density and better fabrication yields. So that's another thing. More qubits per area and improved yields. Uh, Leverage decades of silicon industry tooling and expertise, access to mature supply chain and talent. Then comes more scalable than many alternative quantum platforms. It's more scalable than the alternative quantum platforms. Clear path to value manufacturing. Then comes the fifth one, strategic implication, and lower barriers to scale, but needs fab partnership and target R&D. This align with the existing supply chain and way reduce costs. Recent silicon quantum breakthroughs improved qubit coherence and gate fidelity. Then demonstrations of small scale logical qubits, cry, cryo CMOS control, electronic integrations, better uniformity across qubit areas, then practical procurement focuses. So that are the recent breakthroughs. Then why AGI scaling is hitting limits? Key constraints raising marginal cost and complexity. So these are the main constraints, that marginal cost and complexity. Rising energy and infrastructure cost, power, cooling, and data center build out push up per unit cost. Then diminishing returns from model size scaling. Large models yield a smaller accuracy gains per cost. Then comes the data availability and quality constraints. High quality, diverse databases, datasets are scarce and costly. So, high quality, diverse datasets and scarce and costly. And hardware efficiency bottlenecks, limits of chips and interconnects, slow efficiency gains. Strategic implications, pursues efficiency and hybrid compute, optimize algorithms hardware, and explore alternative paradigms. How silicon quantum can accelerate AGI scaling. Workloads likely to benefit combination, combinatorial optimization, scheduling, in resource allocation, sampling and generative models, faster or higher quality sampling, structured linear algebra kernels, space or block structured solves, hybrid machine learning workflows, quantum sub- subroutines within the classical training loops, energy sensitive niche task, a lower energy per solved problem for selected workloads. Typical AI workstation remaining classical, large, dense natural network training and inference, higher throughput data uh, pre-processing and ETL pipelines, standard matrix multiplication without uh, exploitable structure, real-time low latency serving at scale, mature tools, no, tool chains and frameworks optimized for CMOS hardware. Hybrid classical and quantum AI stacks. Orchestrating GPUs, TPUs, quantum accelerators, and data pipelines. Classical computer layer, GPU and TPUs handle bulk natural network training and inference at scale. Second one is quantum accelerators layer. Quantum processor used selective as accelerator for hard sub problems. Orchestration and control. Classical system or orchestrated training, interference, inference, and accelerator calls. Then comes data pipelines, movement, format, conversation, and pre-processing between layers and latency constraints. Key challenges to overcome the silicon quantum: operational, technical, vendor, and economic barriers that shape the timelines and TCO, total cost of output. Uh, the first one is typically error correction and overhead and uh, qubit counts. Large logical qubit needs extend timelines and increase total cost of ownership. Cryogenic cooling and system packaging. Complex cooling drives capital cost and facility integration risk. Algorithm hardware alignment. Mismatch slows useful workloads delivery and increase vendors selection risk. Economic viability at data center scale. Total cost of ownership uncertainty requires phased pilot and measurable exit criteria. Plausible roadmap for silicon quantum in AI. Short, mid, and long term KPIs with governance guidance. Short term niche quantum acceleration experiments. Short term KPIs performance, energy, integration cost. Short term governance, it could be like cross functional steering. Then, as part of the midterm, reliable, logical, uh, logical qubit and pilot deployment. Midterm KPIs, logical qubit fidelity, uptime, pilot return of investment. Midterm governance, review gates and procurement alignment. Then comes long-term fault tolerance silicon quantum modules in AI stack. As part of long-term KPIs, fault tolerance, scalability, total cost of ownership, long-term perspective in governance, strategic steering and a flexible roadmap, planning guidance, align roadmaps to KPIs and see pilot criterias. Use KPIs alignment and clear success thresholds for pilot. Key signals to watch. Operational metrics to move from pilot to deployment. Logical qubit demonstration. Manufacturing yield improvements. Hybrid AI benchmark results. Energy and cooling efficiency metrics. Reproducibility and independent benchmarks, vendor roadmaps and integration readiness, roadmap milestone, tool chain, and maturity and compatibility, cost trajectory, cost trajectory and TCOs, then signal thresholds for deployment. Define numeric gates to advance from the pilot to production. Key takeaways quantum for practical AI scaling. Silicon quantum enables scale but not limited AGI. One line summary silicon quantums is the most scalable quantum path. Quantum, along with not to create AGI, but can enable the next phase of AI scaling via hybrid system. Pilot targeted workloads run focused pilot on hybrid silicon, quantum inference, and training bottlenecks, governance and integrations, and maintain classical compute investment and define in cross-functional evaluation criteria. Monitor signals, track qubit density, fabrication yield, cost per qubit, and hybrid performance metrics. Why CMOS matters for silicon quantum? CMOS compatibility metal oxide semiconductor foundational chip tech for CPUs, GPUs, memory, sensor, and control. How it work with NMOS and PMOS pairing, complementary uh, transistors reduce static power and improve energy efficiency. So improve the energy efficiency. Cryogenic CMOS control qubits, then strategic implication and manufacturability, mass manufacturability in silicon fab worldwide, CMOS compatible leverage fab tooling. Strategic implication, energy efficiency, low heat and high energy efficiency, support dense qubit arrays. Strategic implication, AI hardware integration. All current AI hardware is CMOS based using hybrid AI and quantum integration. Online takeaways, CMOS is the industry backbone of modern computing, and the reason silicon and quantum has a realistic path to scale. Thanks for joining this session. Thank you.